Hello. In this video, I'm going to go over essentially the second factor that we could look at when it comes to solubility and the solubility product and how that all relates. In this particular example, what we're going to do is we're going to look at how adding what's called a common ion to a relatively insoluble compound affects the solubility of that compound. And it turns out it's an equilibrium process. So again, chapter 17 with acids and bases, and now solubility, it's all about chemical equilibria. Okay, so let me bring up a problem. Let's do it right here. So this one is called calculating the solubility. So keep in mind, not the solubility product. We're not calculating the solubility product. We're calculating the solubility of an ionic compound when a common ion is present. So this one is approached a little differently because we're going to add a common ion. So look in the problem sessions or in the problem sets that you look at to see whether a common ion is present or not. So it says here, calculate the solubility at 25 degrees Celsius of COOH2, that's cobalt-2 hydroxide, in pure water, and in a 0.0160 molar COCl2 solution. You'll find KSP data in the ALEX data table. Round your answer to 2 significant digits. We're going to look at the solubility in pure water, which we've already covered how to do that. And we're going to look at the solubility in 0.0160 molar COCl2 solution. Again, grams per liter. So notice with this problem, they're telling you what units you want to have that in there. Okay. Okay, so let's take a look at this problem. So we have cobalt hydroxide. So cobalt hydroxide, sparingly soluble, not very soluble at all. You'll form cobalt ions and hydroxide ions. Okay, so there's your chemical equilibria. Now, in the first part, they just say calculate the solubility given the KSP values. So let's write out the expression for KSP. Again, it's the concentration of the products, right? And if we look that up in the ALEX data tab, we'll find that it's 5.92 times 10 to the negative 15. Okay, pretty straightforward so far. So remember how we deal with that. To find the solubility from the KSP, this is a solid, so we don't worry about it. This starts off as 0 and 0. Some of the solid will dissolve, so this will go up by x. This will go up twice as much, so it'll go up by 2x. And so then once it reaches equilibrium, we'll have 2x for the hydroxide and x for the cobalt-2. So we can substitute that right in here as x times 2x, and then that's got to be squared, right? Remember the 2 shows up twice. Well, that's 4x cubed, and that's going to be equal to 5.92 times 10 to the negative 15. So the approach we used in the previous section, in the previous problems, was to solve for x, and that would give us the molar solubility of the compound, of the ionic compound. So let's go ahead and do that again. We're going to divide both sides by 4, and that will give us x cubed. And then to find x, we're going to take the cube root of both sides. So far, so good, right? So if we plug all that in, 5.92 times 10 to the minus 15, divide that by 4, Okay. Oops, let me try that again. 5.92 times 10 to the minus 15. Divide that by 4. And then we're going to raise that to, or take the cube root of that. And what we end up with is x is equal to 1.14 times 10 to the minus 5. And the units are moles per liter because the value of the KSP, 5.92 times 10 to the negative 15, is based on concentration units in molarity units, okay? Even though it's unitless itself. That is the molar solubility. Okay. Now, we want to find the solubility, and the solubility is typically in grams per liter. So if we're going to do from moles to liter, moles per liter to grams per liter, again, we're just doing a mole to gram conversion, so we just need to know the molar mass of the compound. So the molar mass, pretty straightforward. We have 1 cobalt, so that's 58.933 grams per mole. And then there's 2 hydroxides, so 2 times 16.00 plus 1.01. That's all in grams per mole. So it's really 2 times 17.01. So that's 34.02 plus 58.933. And it looks like it's around 92.9. So there's your molar mass. Okay. If we want to convert from moles to grams, we multiply by the molar mass. So 1.15 times 10 to the negative 5 moles per liter. So there's your molar solubility. Multiply that by the molar mass. And that's going to eliminate the moles, and we're going to end up with grams per mole. So if we multiply that by 92.95, oops. Let's try that again. 1.14 times 10 to the minus 5 times 92.95. So it's about 1.06 times 10 to the negative 3 grams per liter. They wanted it to 2 significant digits, which is a reasonable expectation. Usually solubility constants and solubilities are only known to about at best 5%, and often it's not even that good. So really having more than 2 significant digits is probably inappropriate. And so we'll round it to 2, and there you go. So there's your basic, oh, let me be careful with my language. There is your regular old-fashioned solubility of cobalt hydroxide in water, okay? Now, in the second part of this question, what they ask us to do is to find the solubility in a different solution. So instead of putting it into water, we're going to put it into a solution that has what's called a common ion. So let me bring back the question so that we can evaluate the second part. The solubility in 0.0160 molar cobalt chloride solution, CoCl2, again, grams per liter. So this is a very common type of problem. What we're doing now is we're saying we're not going to be just in water. We're going to be in water, but we're going to add a common ion to it. And what you want to be able to do is identify what the common ion is. When I say common ion, I mean an ion in the solution that is in the compound we're studying. The compound we're studying is COOH2, cobalt-2 hydroxide. That's the compound we just calculated the solubility for. But there's another compound being added to the second part, and that is COCl2. And notice its concentration is given. Its concentration is 0.0160 molar. This has cobalt in it, right? It has chloride, Chloride, it turns out, doesn't affect much here, but it has cobalt in it. Cobalt is a common ion. It's one of the ions that's in our cobalt hydroxide. So that's why we would call this a common ion problem. So the thing about cobalt chloride is that it's a chloride salt, and you may not remember your solubility guidelines from Chem 11, but cobalt chloride, chlorides in general, are very soluble in water, at least relatively soluble. So when we try to dissolve CoCl2, it will dissolve in the water. And the result of that is we will now have cobalt ions dissolved in the water. That cobalt ion solution will affect the solubility of the cobalt hydroxide. So in other words, if you add a common ion to the water, in this case cobalt, that will affect the solubility of the compound, in this case COOH2. Now there's a second common ion, but it's not being used in this problem, and that would be the hydroxide ion. If I were to add hydroxide or remove hydroxide from the water, now how do you do that? How do you change the hydroxide concentration in water? Well, one way is to change the pH, right? If I were to add a strong base, sodium hydroxide, that would change the hydroxide concentration. That would also affect the solubility of COOH2. Okay, so adding a common ion, doesn't matter which one, either the cobalt or the hydroxide, adding one or both of those ions will affect the solubility of that compound. Now, I'm going to show you how it does. We'll go through this. We have to be able to calculate it. I've said that it will affect it. You'll see by the end when we look at the answers and make a comparison that it does affect it. Okay, so here's how we approach the problem. So this is, your sort of part 2, right? So we take the same chemical equation we did before, and we rewrite it. And we rewrite our expression for KSP. None of that has changed. The thing about the solubility constant, the KSP, it doesn't really change unless you change the temperature. If you don't change the temperature, it remains pretty constant. So that aspect of this is not going to change. What will change are the details here. So let's go through our initial change in equilibrium. The thing that happens here is this doesn't start, remember, it's a solid, we don't worry about that. This doesn't start at 0 anymore. And the reason it doesn't start as 0 is because we're adding cobalt chloride. Okay, so it's going to start off as 0.0160. That's the key difference here. We're adding cobalt chloride, which dissolves in water. So if it dissolves in water, we're not worrying about its solubility constant, its KSP. It just dissolves. So you're going to get 0.016 molar. I didn't put the M for molar, but that would be molar for the cobalt ion. Now, hydroxide is unaffected so far because we didn't change the pH or anything. We just added cobalt chloride. The chloride has no effect because the chloride is not in this equation. So you can ignore the chloride. So only one of the 2 ions is important here, and that's the cobalt. So here's what happens. Again, just like with all of the discussion we've done in chapter 15 and 16 and now 17, there are no hydroxide ions. So the value of Q, reaction quotient, is 0, right? Like if you don't have any of one of the products, Q is 0, which means that Q is less than K. And if Q is less than K, then the reaction proceeds to the right. Right? It's all the same principle. So far in this course, mainly what we've been doing is equilibrium. So now this becomes 0.0160 plus x, and this becomes 0 plus 2x, which is just 2x. Again, this does not affect the value of KSP. It will affect the solubility x, but it doesn't affect the solubility constant. So this is still the same approach. 0.0160 plus x, and then 2x, but again, remember that 2, we got to square it. Now, this is a bit of a challenge mathematically. We have an x in one term and a 2x in the other term, and that's squared. So it's actually our highest order for this particular function is x cubed. It's a third order polynomial, which are not simple to solve. However, again, we can apply some chemical principles to our logic here. The value of KSP is tiny. 5.92 times 10 to the negative 15. So if you logically think about these numbers, what would x have to be for this equation to be solved out? It's not going to be very big. In fact, in the previous problem, it was 10 to the minus 5. It's probably somewhere around there, maybe actually smaller. And so in a sense, x is very, very small in this problem. So if I say, I'm going to take a number which doesn't look real big, and I add to it a really, really small number, vanishingly small. Imagine it becoming 0, right? If x is really small, less than 5% of 0.016, we can make an assumption. We can say that the KSP is 0.016 times 2x squared, right? Because again, even though the numbers are different, if I have $1 million and I say, okay, I want you to do my accounting and I'm going to add $1 to it, the dollar just doesn't affect the bottom line very much. Same thing here. If x is much less than 0.016, then that's going to be the case. We can just ignore it. So what this becomes then, remember, you got to square what's in here in the second term. So this is 2 squared, which is 4. Times 0.0160. I'm putting the numbers out first, and then you're going to have x squared, right? And 4 times 0.016 is 0.0640, and then you're going to have x squared. And that's going to be equal to KSP. But remember, KSP is 5.92 times 10 to the minus 15. That's the value of KSP, right? Don't forget that. So now what can we do? We can solve for x, but notice this is not arithmetically very difficult or algebraically very difficult, right? We don't have to worry about the x cubed term and using, some more sophisticated algebraic methods. We can just solve using square root. So I'm going to divide both sides by 0.064. And that's going to give me x squared. And then I'm going to take the square root of both sides, right? Square root of this, square root of this, and that will give us the value of x. Okay. So it should work out pretty nicely. Let's see what we end up with. 5.92 times 10 to the minus 15 divided by 0.064. And it makes it a little bit bigger, but now we're going to take the square root. And notice we get for the value of x. See, it is pretty small, right? So even if you said, look, I don't know about your assumption of x being small and I can ignore it, you'll see here it actually does work out okay, right? It's really small. Even if the value of KSP were 10 to the minus 10, it would still be a pretty good assumption here, okay? Or even 10 to the minus 6 or 5. Really, for solubility, constant calculations, you can generally get rid of the term that's in there. Okay, now remember again, this just like in the previous part, this is moles per liter. So if we want to calculate grams per liter, again, we have to multiply by the molar mass. And our molar mass, I think, was 92 point something, right? So it was 58.933 plus 2 times 17.01, 92.95. So I'm going to take our molar solubility. Remember, this is molar. 3.04 times 10 to the minus 7 moles per liter. I'm going to multiply it by the molar mass. And that's going to give us, let me multiply that by 3.04 times 10 to the minus 7. And it is 2.8 to 2 significant digits. 2.8 times 10 to the minus 5. Oops, the moles are going to cancel. grams per liter. Now I want to box that off, and I'm going to compare it with part 1 when we did it, just in water. In that one, we got 1.1 times 10 to the minus 3. Okay, take a look at what happened here. In water, it was 10 to the minus 3 grams per liter. Not very soluble, but if it were toxic, 1.1 times 10 to the minus 3 grams per liter would be very bad. But look what happens when we have the common ion. By adding the common ion in this problem, we've lowered the solubility, right? The math speaks for itself. The concentration of the solid that dissolved into the water in this part 2 was 10 to the minus 5. So smaller by, I guess, a factor of about 50 or 40, something like that, 45. Much less concentrated, so much less soluble. So you actually get a lower solubility when you have the common ion. So sometimes people call that the common ion effect. Essentially by adding that common ion, the cobalt ion, that lowered the solubility of the COOH2, the cobalt 2 hydroxide compound. Likewise, if we had made the concentration of hydroxide higher artificially by, adding some strong base like sodium hydroxide, that also would have lowered the equilibrium concentration of the solute here. Okay, it would lower the solubility. Okay, so your take home there is that if you add a common ion beyond what it was in water, if you increase the common ion's concentration more than it was in pure water, that will lower the solubility of one of these compounds. Okay, so that does it for our discussion of solubility.